first participant is Jason from Malaysia, and he will show us my new FPGA board with Forth. Jason, are you ready?
Yes, I am.
Go ahead.
Okay, right. Yes, I will share my screen. Peter, I think you need to stop sharing so that I can share. Okay. Well, there's been a lot of talk about FPGAs recently. We had quite a few sessions with Klaus, different Klaus, and let me share the. I'm gonna share the whole screen. So I've got a whole bevy of boards here. A lot of the FPGA boards that we've seen, we've seen quite a few, but they're actually quite pricey, right? And it brings up the question of, okay, if you're gonna spend $50, $70, $100, is it going to be worth the while, right? I think when you get into FPGAs, you probably have to have a real reason for it, right? Because it gets to the point where you have to debug the CPU as well, right? Why use an FPGA? You might want to have a CPU with particular capabilities like peripherals or something. But that means debugging the CPU as well as your application, right? And possibly the Forth as well, because you probably have to customize your Forth to that soft CPU. But anyway, if we look here on my screen, oh, hello. Yes, we'll just move the cat out of the way. Right, thank you. So the journey actually began with this one. This is called the ice stick from Lattice. It has a fairly small FPGA on it with just 1,280 lookup tables on it. When it was introduced, it was very interesting because it was a $20 FPGA board. And it has everything you need on it. It has the FTDI on it, not a lot of I/O pins, but enough to get going on something. These days, you'll be less lucky because they cost about $75. Probably because of well, whatever. Well, a lot anyway for 1,000 LUTs, right? So that led me to try to search for something else, right? You can now get these. These are actually from the same family of Lattice FPGAs. You'll be amazed. Actually, okay, cat attacks again. The FPGA is actually this very small chip right here. The smallest chip on the board. I wouldn't like to solder that. This costs about $20 or so. But that's part of the challenge, right? I mean, if you really wanted to get serious about using FPGAs in all your projects, then cost and accessibility becomes a real problem, right? So that led me to experiment with this. So this is actually another Lattice. And what makes it interesting is that unlike a lot of other FPGAs, it's actually, you can call it a single chip solution. This can be powered from a single voltage rail, 3.3 volts only. You don't need 1.2 volts and 2.5 volts and all the other power rails. It has built-in user flash. It has built-in the block RAM as well, of course. It has the cat is very needy tonight. Well, basically, and it has onboard oscillators as well. So literally, you have your own program storage, user program storage there. You've got the oscillators on board, and I had this going for a while. This was my proof of concept that ran on a breadboard. I haven't got the breadboard set up anymore. And then later on, I progressed to this. So I've been prototyping this. The last thing we heard was that I managed to burn the FPGA that was on here, and I've since removed the FPGA, checked the board out and all that. Well, I'll get it up and running again soon. So the next question will be, okay, because all this continues along the lines of, is it worth my while, right, for the average Joe to start playing with FPGAs? There's obviously a certain eroticism involved, in being able to say that you run your Forth code on a Forth native CPU, right? So that's really what all this is about, right? Oh, we are determined today. Okay. Okay, right. So I'm going to start this. So further benchmarks in Forth. We had some benchmarks before where we saw that the ESP32 Forth running simple integer benchmarks was able to put in something like anywhere from 3 million to 13 million words per second, which is very good, which is very, it's possibly all you'd ever need. So what are we after this time? If you remember, my approach is that I'm not going to go into a lot of optimization, because I think it's good to give people an impression of what they can expect out of the box, right? I mean, instead of saying that, oh, well, if you have to, after you do all this reading and you experiment with it for a month, then you'll be able to optimize it to get this kind of performance. No, that's not what I was hoping to show. So this is really, open the box, download the pre-built bin file, program the bit stream into the flash, and take it for a spin. What do you get, right? So this is what I'm trying to show here. Okay, so the four contenders I was trying to have was, of course, we have the ESP32 Forth that I had running on the regular ESP32, but also the C3 as a reference still. And then I have MiCrisp Stellaris running on an ARM Cortex M0. And then I wanted to run MiCrisp Ice on the Ice stick. Now, MiCrisp Ice would have been interesting because it adds something that is missing from the swap Forth on the J1. The swap Forth on the J1 requires you to essentially rebuild the hex file for your user application, and then re-synthesize the Okay, somebody might have to mute the microphone. Yeah, thanks. So but MiCrisp adds its own instead of replaces swap Forth with MiCrisp, and adds in a bunch of commands: erase, load, and save. So erase, load, and save basically adds in the runtime updating of the user flash area that we were all looking for, right? I mean, this is one of the problems that we've always had, with the other FPGA implementations of Forth, that essentially you had to rebuild the whole bit stream just to integrate your custom user code, right? So MiCrisp is promising, and it does, in fact, it does do that, but unfortunately, I couldn't get any form of loop to complete. It will hang after the loop. So at this point in time, I'm still looking into that issue, but instead what I've done is I'll show some results from running the J1A from James Bowen. So both the ARM and the J1A are running at 48 megahertz in this case. And then how did I do the timing on the J1A swap Forth? Actually, James provides a hash time command in the Python shell, which provides a millisecond level timer. The resolution claims to be millisecond. To be honest, I always see it give results in the multiples of tens of milliseconds. But it's good enough for our purposes, I guess. You can actually run swap forth untethered. What happens is that the shell gives you things like command history and things like that. So you don't absolutely need it, but it was useful in this case for the test. And then MeCrisp on the ARM, it actually has a 21 megahertz built-in SysTick timer. So that's what I've used. Of course, ESP32 Forth has the ticks word. Okay, so what did I test out? The last time I had very, very simple tests, right? I just had basically, I think it was pi, the value of pi or something like that loaded up, and we looked on that. So not a great deal. So it's not surprising that it could do a lot of loops per second on that. So this time I thought I'd try something more interesting. And in this case, I wanted to try out the typical fixed point operator, right? The multiply and divide. I forget if there's a proper name for it, but it's used a lot for multiplying or dividing fixed point numbers together and readjusting the fractional side, right? And what would we use this for? This again, the part of the reason is because this is something that would be used in something that has been cropping up a bit in the forum recently. It's like using Forth for AI. I'm not sure if that's really works well or not, but if you're doing AI, then you would need a dot product and the normalization functions, and you might probably need to use this, right? If you're using 16-bit or 8-bit quantization. Other possible benchmark candidates might have been the prime sieve or so on, but in this case, what I've done is I've implemented the Newton-Raphson square root search, a non-recursive version, because I didn't want to have an unpredictable number of iterations, right? And in fact, anyway, at Q8 fixed point resolution, the result converges quite quickly anyway. After about 2 or 3 iterations, the result will converge on the final number. Okay, so this is the code I used. I redefined my own multiply and divide words for that, simply to avoid dependencies or whatnot. That was the initial idea anyway. And then I have the fixed point square root function, and then after that the benchmark itself. Oh, I've got a missing bracket over here. So I've got 3 versions of the benchmark. I've got 3 different versions of the benchmark, and actually they're all the same. The only difference is providing the different code to do the timing on the different platforms. Yeah. The last one being, of course, using the SysTick timer register locations for the ARM. Okay. So now one thing that has already cropped up is that because of the use of the multiply and divide operator,
//
yeah, // Okay, thank you. // operator. It sort of it highlighted a lot of differences between the different microcontrollers being tested here. As in, does it have hardware multiply or divide and so on, and that had a huge effect on the benchmarks, as you'll see in a bit. There's some nuance to it, basically. So that's a bit of interesting things there that you have to take into account if your application needs a lot of multiplies and divides. And this is just to restate what I used and the versions that I used. I tried MeCrisp ICE 2.6C ND, but neither of those versions would complete a loop. So I don't know what's going on there. I haven't had time to study the MeCrisp Forth sources yet, but swap Forth does it nicely. Okay, so right into the results. Nothing for MeCrisp Ice, but J1 Salt Forth turned in basically 6,410 iterations per second. Right? Oops. J1A Salt Forth turned in 6,400 iterations per second, while the ARM turned in 2,500 iterations per second. So quite a lot slower. And ESP32 Forth turned in monster values of like between 55,000 iterations per second for the C3. Not really surprising given the lower clock speed, and 82,000 iterations per second on the Tensilica version, running at 240 megahertz. And if you switched to using 4Next instead of do loop, it would give you another 8% on top of this to bring the figure up to 89,000 iterations per second. So yeah, this is a bit surprising. You know, I would have expected the ARM to do better, but you have to remember that this ARM, I believe they have the M0 plus, they have multiply instructions, but they don't have divide instructions. So all of that would have been done in software, and it comes down to how that person implemented it. And it in all cases, the / operator tends to, if I'm not mistaken, tends to use double words in between, right? Otherwise, the result simply would not have come out right. So that would have been a factor as well, because in the middle of it you'd have twice as many operations as otherwise. Okay, so we mentioned about some of that nuance, right? Now, if I got rid of the multiplies and divides, right, and changed it to basically adding an array of two numbers, basically, or just adding two numbers together, then the number changes drastically, right? All of a sudden, the ARM is able to do 3.5 million iterations per second, and the J1 is at about 1.96 million iterations per second. Right? So we can see that not having a dedicated multiply and divide instruction makes a massive difference here, and that comes back to the whole question about FPGAs, right? These are all small FPGAs, and so you wouldn't find a very rich instruction set on these ones, right? So both the EP16 from Dr. Ting and also this J1A have a very limited instruction set. I think Peter was saying that the EP16 doesn't seem to have shift instructions on it, which will complicate some algorithms, right?
The shift instructions are operations of the assembly language of the EP16, but they are not present on the eForth.
I see. Interesting. Okay, so there you have it. It becomes a situation where number one, if you ESP32 Forth rocks is one thing. And if you were to choose your application, choose very carefully. Be careful of M0s. They might not, they won't perform very well if you have a lot of multiplies and divides, and you get a sense of what the FPGA soft Forths can do. But bear in mind another thing though. So what happened here? Both the M0 and the J1A were running at the same clock speed, right? And they essentially both running machine code because the MeCrisp on the M0 is compiling into ARM thumb machine code. But the ARM is pipelined, so whereas the J1A is not. There are different versions of the swap Forth CPU that are pipelined, but the J1A is not, simply because the iStick doesn't have enough lookup tables to accommodate a pipeline architecture. Okay, so that's what we've concluded here. Basically, if you know the current crop of FPGA soft CPUs, other than perhaps Klaus's microcore, don't handle complex computations very well. But if you're just operating on standard I/O, simple manipulations, occasional multiplications, and all that, they'll do quite well for you. But there'll always be, I suspect that for most people there will always be this question of, well, ESP32 is so fast, right? For the price. So in fact, what you see here is that that will really, do almost everything you need, unless you really need the massive I/O pin count of FPGAs, or you needed a special interface a special device, maybe I/O peripheral to your Forth CPU. Then the FPGA will be the one, right? And this is the sort of performance that you can expect. All right, thank you. That's the presentation I've got.
Great, Jason. Excellent.
And yeah, and I hope that we can get this. This is one of the reasons for developing this simple board, is so that people can have a low cost and simple FPGA board, right? Otherwise, we're always facing a case where you have multiple voltage rails, you need multiple chips and all that, and the hope is to make something as simple as the ESP32 board, right? Honestly, will never be as cheap as China, but this is about as close as you get, especially when you consider that this is like $75. This is 25, right? So this is hoping to produce something that will improve the accessibility to everyone. Anybody have any questions?
These numbers are impressive. I don't know. Probably we should make in the next meetings new benchmarks. Show other benchmarks, not only. Francois has a question. Go ahead, Francois.
Yes, Jason, did you try to normalize this with respect to power consumption?
No, I haven't yet. That's something that Peter's been giving some suggestions on methods to measure power consumption. There's one obviously the simple way is just to hook up a microamp meter or milliamp meter to the project. But me being me, I started to dream of having a current logging system, and thought to have so that means that it'll take me months to get it done. But it's on the way.
If your board is USB powered, you can use one of those USB meters. They work fine.
Yeah, yes, I have one of those, and the challenge is that it registers 0.
That's hard to beat, of course.
Basically, those I have one of those USB power monitors, and it seems to have a smallest resolution of like 10 milliamps. So below 10 milliamps, it doesn't show anything. And it's the same problem I have with the ESP32C3 actually. If if you're not using the Wi-Fi and just using Forth and the C3 as a CPU, then it registers nothing.
Yeah, Wi-Fi is a bit. That Wi-Fi is 200 milliamps minimum
Yeah.
when active.
Yeah.
Jason,
Yeah.
can you tell the group which FPGA you are using on your own developed board, please?
Oh, so this is the Mark X02.
Okay.
They're available in QFN. Yes, I did have to go through a few rounds to get this soldered on with no shorts. They do have them in BGA and QFP packaging as well. So 100 pin and 144 pin. They have them all the way up to 7,000 LUTs. They've got versions that require multiple voltage rails, but the HC variant will give you the single voltage rail. I can pull it up on the.
Jason, would you be able to put a link to maybe the data sheet in the comments section, please?
Yes, certainly.
Thank you.
It doesn't have multipliers. RAM is not huge, but it does have a built-in SDRAM controller. And it does have built-in timer, SPI, I2C, and a few of these things. So quite amazing. And this this particular one that I've got here, with 1,280 LUTs and 8 kilobytes of embedded block RAM and 8 kilobytes of user flash as well, but potentially up to 12. This costs $7 from Farnell in single quantities, and if you buy 20, you can give them a call and say, hey, can you be nice, and they've given some nice discounts before, so it's I'm hopeful, because once you have it in some sort of form factor like this, I mean, you've seen the other, the RZ EZ boards and all that. They're very great for learning. They have built-in 7-segment displays, but when you start to want to take this from learning to integrating it into some sort of real life project, then you want this sort of like an Arduino Nano kind of form factor, where you can design the rest of your board, build up your board using strip board or perf board or something, and just plug this in, right? So that's the inspiration for this. That's what I felt was missing.
Yeah. I know that we've had a discussion about multiply and divide. I mean, it wasn't until the introduction of the 8086 and the 68000 that microprocessors actually had multiply capability. And of course, if you go back a decade from then, there were always algorithms available that would allow you to do scientific and transcendental functions using chordic arithmetic. So, I mean, at the end of the day, we went to the moon and back several times on a 16-bit processor that had no multiply instruction. So, if you go back in history far enough, you will find that multiply and, more to the point, divide have been definite luxuries within the instruction set, and often only the reserve of large mainframes up until about 1980, when super minis were appearing.
Yes, definitely. I seem to remember that on the 8086 divide, integer divide took anywhere from 70 to 90 clock cycles.
Yeah.
But all of that was microcoded anyway. It didn't really have it, if I'm not mistaken, it wasn't hardwired, right?
No. And certainly a hardware multiplier, if you're short of lookup tables, LUTs, it's a bit of a luxury.
Yeah.
When you implemented the J1A in the Mac O2, what was the LUT count? Do you have an indication at all?
I haven't been trying the J1A on the Mac actually, but I tried to put the EP16 into the ICE40, the 1K ICE40, and that failed. It stated that it needed something like 1,900 LUTs, so it wouldn't fit. Surprisingly, it fits on the Mac. I can't explain that, even though it has the same number of LUTs, but presumably the logic block resources are different somehow, right? Yeah, well, we could find out if we go and study the datasheet, but no, I didn't. Yes,
Yeah, because
the EP16 fits.
I'm assuming that on the lattice Mac O2, the LUTs are 4-input LUTs. Yeah.
Yes. Yes.
If you were to go for a Xilinx FPGA, they have 6-input LUTs, which
Yes.
gives somewhat greater flexibility with logic design. Yeah,
that's right. And they can be partitioned in two as well. So
yeah.
a lot of flexibility there. Yeah, that's right. Yeah.
Thank you.